Um, I would like to point out something. There are 19 of you in this class. This is the recording from Monday, the one I did in advance, so that you could have the teaching demonstration from Dr. Al-Salwi. I promise I'll get it right eventually. There are 19 of you in this class. Why has this video only been watched 9 times? So some of you are going to be lost today. So you better go back and watch this and then watch today's again. All right. We were talking about trying to determine the complexity of an algorithm. And I ended with this one on distances. So this is a piece of code that takes a set of coordinates, x1, y1 through xn, yn, and compares the distances between them. And I'm looking for the smallest distance between them. And there are 6 operations in this line. I've got 2 subtractions, 2 squares, a square root, adding. Got a comparison as well, separate from the operation. So technically, if I count that, there's also a 7th thing here. But just counting how many times we run through our loops, I'm going to go n times through I. But for each of those i's, j increments as well. And really, that means I've got 2 loops. They're both operating at linear speed. I'm going from 1 to n. I'm going from something to n. If I add up all the times that's n plus 1 over 2. Sorry, in this case, n minus 1 over 2. Because I'm only going through n minus 1 total. And that's big O of n squared. And that's measuring the distance between connected points, sets of points. And I mentioned this was related to my research area in distances, Hausdorff distances and fractals. But this is just where I came up with an algorithm that I was interested in. And as we saw from the teaching demo on Monday, a lot of our searches are big O of n squared in their worst cases, but we can use recursive ideas to try and make those better. How does that make something better? The binary search was given as the example. Because the binary search cuts my list in half every time. Step 1 takes me to n over 2, cuts that in half, and then I'm going to cut it again. Eventually, I'll get down to just 1 element. As long as I deal with even integers, eventually this goes to 1. But if I think of that as working backwards, I would have had 2 in the list before that, would have had 4 in the list before that. Those are powers of 2. Well, they're all 2s, but how many are there? There's whatever number of 2s to make this number bigger than n. Or at the very worst, equal to n. But that's asking for an exponent. I want to know what value of k makes that bigger than or equal to n. Well, that's 2 to the k bigger than or equal to n. Oh, I need to get the power out. That's how I could use a logarithm. There we go. So it turns something that was quadratic in time or linear in time to something that's smaller order. And that's really the piece that matters. The relative size of my order. Page 238. Bottom of this page, there's a list. And remember, if you've got direct access to each element, like you do in an array, give me the 7th item. That's big O of 1 because it takes 1 command to go get it. Find me number 7. I'm done. If it takes log n, logarithmic complexity, n log n, and then all the powers of n come after that with logarithms in between them. So n squared, then n squared log n cubed log n. You can also include log of n. You can look at polylogarithmic behavior like that. You won't see that all that often. But I drew a line here. The last two. B to the n, some exponential function, or an n factorial. These are fundamentally different than these. Everything that's up here is at worst some polynomial. If you think about n cubed log n, you can really say, well, that's smaller than n to the fourth. So it's smaller than a polynomial. N squared. N log n is a little bit smaller than n squared. So it's at worst a polynomial idea. These are bigger than any polynomial as we go off to infinity. So this whole class are called polynomial complexity. And then these two at the bottom are called non-polynomial, P and NP. So the non-polynomial realm is a much more complicated type of problem. So let me think about what some of these problems are. Here's a question for you. Excluding Hawaii and Alaska, I want to visit all 48 state capitals. I am a cheap mother. How do I find the cheapest trip? Okay, so I could try and start looking at the distance, the path of minimum distance. What's the problem with that? I mean, we're here in Greensboro. I'm going to make an assumption. Let's start in Harrisburg, right? You go east or west? Go north or south? Which one's closer? I know the answer to that. You all have Google in front of you. You could figure out, is the capital of Ohio closer than the capital of New York? Wait a minute. I skipped over West Virginia and Maryland and Virginia, didn't I? What's actually closest? I don't know. But at some point, I'm going to start going north and east, aren't I? And then I'm just going to hit the closest capital. What's going to happen? At some point, I'm going to get stuck up in Augusta, Maine. And then I'm going to have to take a big jump somewhere else. And that's going to be the expensive piece of the trip. It turns out the only known way to find this minimum true distance is to list them all. All possible trips. Here's a question for you. How many is that? All I need to do is count them. I don't even need to work out the cost at the moment. Let's just list how many options are available to me. Again, I'm assuming that we start and end in Harrisburg. That? Almost, because I've decided which one's going to be first. There are only 47 left, right? So there are 47 states I could go to next, because I start in Harrisburg. Then there are 46. Then there are 45. Oh, crap. This is an n factorial problem. Now, I wanted to visit the 48 continental United States capitals. That's why it was 47 factorial. It's still roughly big O of n factorial, right? If I wanted to visit all of the cities in the state of Pennsylvania with populations over 100,000, I don't know how many there are. Do a quick search on the census database at the Pennsylvania Department of Interior. I can find that out. Same deal. I want to deliver packages. I have to visit all these businesses. What's the cheapest route? Personally, I don't care. But I don't work for UPS or FedEx or the United States Post Office. If I want to be efficient about this, if I want to do this correctly, I need to know what the cheapest route is, what the most efficient behavior is. And this is going to take forever to write out. Somebody grab your calculator. Tell me what 47 factorial is. While you are on the internet, I would like you to look up some other number for me. Ready? I'd like you to look up the age of the universe in seconds. What's the age of the universe in seconds? That's 42 more digits long than the age of the universe in seconds. If you could write out a billion of these routes a second, and you started the minute God said, let there be light, you wouldn't be done. You wouldn't be 1% of the way through yet. That's too complicated for human beings, right? That's the problem. Polynomial problems are called tractable problems. And those problems make up the class P in that list on page 238. But problems like this one, the traveling salesman problem, is what this is commonly known as, are intractable. Problems that are intractable under any currently known implementation of any algorithm we could find are potentially going to take longer than the lifetime of the universe itself.
Then how does my Google Maps show me the quickest route to where I'm going immediately?
Because it doesn't. It fakes it really well. What it does is it gives you an approximate. It says the fastest way from here to here by the data we've already collected has been this route. And that's why your GPS or Google Maps or Waze or whatever routinely goes, something has changed, recalculating. Because it's all of a sudden, something came up and there's a new data point at it. And you drive up and there's a road closure and you didn't know, and it didn't know, and now it goes, okay, you turned somewhere, I don't know what's going on. And what it's doing is approximating. And that's the difference. In a lot of these intractable problems, we can get an approximation in polynomial time. And given a large enough computer, or a series of computers, or historical data, I can use those approximations very well. But most problems that are labeled intractable are problems for which we literally have no known algorithm that will solve it in a reasonable amount of time. Why are you told to change your password every so often?
So that nobody will break into it.
Because IT is just being paranoid, right? I don't need to do that. And that's why, you know, until recently, you could actually go ahead and make your old password, your new password, the same as your old password, right? You log into your Seton Hill account. What's the minimum length of your password? Like 12 characters, I think. At least one uppercase, at least one lowercase, at least one number, at least one symbol, right? 12 characters, lowercase and uppercase, 26, and 26 is 52. Digits, 0 through 9, that's 10 more, so that's 62. And then all the symbols. There are a lot of symbols on here. I think like 15 or 18 of them are actually usable. You can't always use semicolons depending on what language, or you can't always use an exclamation point. It depends on what restrictions they've got. 72 and 15 is 87. So let's say there were 85 characters that you could use for your password. 12, 85 choices, right? 85 times 85 times 85, multiply. What's 85 times 12? Well, 85 to the 12th. Again, let's assume I can make 100 million attempts a second, right? So I'm going to divide this by 100 million. That's 1 million, 100 million. 100 million attempts a second means it's going to take me this many seconds. How many seconds in a year? Where are my musical theater people at? Come on. That's minutes. So I have to multiply by 60, and that means 31 million. 31 million is smaller than that number. You have to change password at least once a year. It's guaranteed to be secure. It's a tractable problem, but it's unreasonable to actually brute force your way through somebody's password. And that's why brute force algorithms, it's an algorithmic paradigm. I mentioned that in the video. It's a way to think about making an algorithm work, but it's not reasonable. It's not often tractable. Some problems, oh, wait a minute, I didn't finish this down here. This is the class NP, non-polynomial problems. Some problems are even worse than this. There are problems for which we do not know an algorithm to solve them. Believe the person responsible for this It's a guy by the name of Alan Turing. Anybody know that name? What are you going for you? What are you going for? Right. The movie with Benedict Cumberbatch playing Alan Turing, I've forgotten the name of the movie. Yeah, he's a theoretical computer scientist, and he was known for code cracking, because code cracking clearly is not a tractable problem in an easy fashion. You need some sort of snuck-in key. You need to be able to break something. We'll talk about encryption in more detail in several other courses. We'll talk about pen testing and its relevance to these sorts of algorithms on Monday. Turing said, here's an algorithm. What were our definitions over a week ago? What are requirements for an algorithm?
It has to have a set input and output.
Okay. Precise set of steps. And it had to give you an output. It had to finish and say, here I am. Here's a question. Does this algorithm finish? Does it halt at some point? Turing said, I now want to take this question and ask it arbitrarily. Here's an algorithm. Will it halt? Here's a different algorithm. Will it halt? You're not allowed to run the algorithm. You have to read it, but not run it. Because if you run it and it doesn't halt, you're never going to stop. And it could take 137 billion years, and you won't be around to check if it halts. Does this algorithm actually halt?
Does it do all that at the same time?
That's a really good question, because right now it's supposed to, but nobody knows if it works beyond a single atom qubits. While we have created qubits that could bypass this deterministic algorithm idea, we haven't been able to implement anything on a quantum scale. If quantum scale computing becomes absolutely feasible, all of this, everything I've talked about today, goes right out the window. You know what goes with it? All the privacy you've ever had, gone. No password will ever be secure. No biometric data will ever be secure. Your bank records will be public domain. Your dirty little internet searches will be public domain. Nothing you do will be hidden ever again. You should only hope and pray that quantum computing fails. It's horrible. It's a brilliant idea, but we're all in deep if it happens.
I think everybody's gonna have to get off the internet except for like manufacturing things that are gonna be clothing out of water, because they're gonna be able to force it into existence.
I was about to say, this is where the replicator in Star Trek idea comes from. This is a brilliant, wonderful idea. Oh, the computer just does its magic, I don't care about it. This is going to make AI look like a walk in the park, people. Because if you put a quantum computer AI piece together, it'll build itself. And we won't ever put that gene back in Boston. So I love all of you computer scientists wanting to work on this. I'm warning you now. Watch carefully. However, there's another question that is legitimately askable. I came up with this traveling salesman problem, and we figured out that right now the brute force algorithm is big O of n factorial. Is there another algorithm somewhere that I just don't know that would be polynomial? Maybe it's n to the 400, but that's still polynomial time. And the general version of this question is, are these really two different classes? Are there really polynomial problems over here, and non-polynomial problems over there, and never the twain shall meet? Or are these two classes really the same? Again, this is an open problem. Are untractable problems untractable because we don't know the algorithm? Intractable problems. Or are they truly beyond our ken through any polynomial algorithm? By the way, this problem right here is currently open. In the year 2000, Clay Math Institute issued 7 challenge problems. In the year 1900, David Hilbert at a conference did the same thing with a little over 24 problems, I think 27. And Hilbert said, these are the problems that will drive mathematics and computer science research for the next 100 years. And people started looking at these problems and saying, I don't know if this is understandable. And people started answering them and working on them. Some of them were solved as recently as 1995 or 2010, 2018. Some of Hilbert's problems are still unsolved. The Clay Math Institute said the same thing. And then they put the money where the mouth is. And they put up $1 million prize for each of those. Each of those 7 problems has $1 million prize on it. You want to make your fortune in computer science? There's your way to do it. One of them was solved so far this millennium. I think it was early 2000, 2006, 7, somewhere in that range. A gentleman addressed one of the problems called the Poincaré conjecture. Summaries of all of the problems are available at the Clay Math Institute website. And he wrote a series of papers, which after a lot of review, people said, yes, I buy this, this works. He turned down the money. By the way, you already know an exponential problem. Fill out a truth table. Every additional statement doubles the number of rows, right? So if I have a polynomial with n variables, a proposition with n variables, filling out the truth table is 2 to the n. Crap, truth tables are non-polynomial complexity. That's why we only did small ones. Questions? We can always trade off space for time. I've only talked about complexity in terms of the number of steps something takes. You could reduce the number of steps by writing out a lot of the steps you're going to need in your algorithm and storing them in memory. And then just having to pull them by going to the right element of the array. Oh, that one, that's the thing I need. That's the space complexity idea we talked about in the video. And the reason is that memory used to be really hard to come by. It used to be very difficult to build a hard drive that would store any information. In 1965, do you know the size of a 5 meg hard drive? It was the size of the podium here. There's a picture of them loading one onto a plane in the airport in 1965. I kid you not. It's got 5 guys around it. It's strapped to a hoist. They're putting it in the cargo of the plane. It's this big. Now, you fit 2 terabytes on your thumbnail, right? So space has become cheap. If I preload a lot of these options, I can bring down my time complexity to just searching through all my options. We know searches are big O n squared. So there's easier ways to trade off. Can I make this trade-off for intractable problems, for non-polynomial problems? Can I trade off enough Space. Well, how much space does it really take? Now we start to ask, again, another quantum computing issue. How dense can I make my storage space before it's no longer used? TV police procedural dramas. Search the phone records. Question for you. How many phone calls do you think were made today from campus? Somewhere, I have no idea, right? How many of your cell phones, right? The cell tower location right around us. Wait a minute. They do these on the federal database. Federal crime shows all the time, right? Go search the phone records. Let me assume I'm going to store 5 pieces of information. Outgoing phone number, target phone number, time of call, length of call, character. Just those 5 pieces of information. If I did that for today, just today in the United States, I'd get somewhere between 800 and 1,200 terabytes. If I do it for the year, I'm looking at petabytes of information, potentially exabytes of information. Searches of that much, it's impossible. Just the tractability, even if it's big O of n squared, you're now talking about 10 to the 30th operations to search. Again, it's longer than the lifetime of the universe in seconds. As we increase our computer speed, here's an order of magnitude chart for the size of our n, right? Now, by the way, this is not a new book. This is a fairly old book. This is like 2022. So I'm sure these numbers are out of date. If my problem takes log n time, 10 operations at 10 to the 12th per, 10 to the negative 11 seconds, right? That's gig processing speed. Your MacBook in front of you has a 2.6 gig chip in it, right? That's reasonable. It's about right. N, okay, it'll take 10 to the negative 10th seconds. N log n squared, n factorial, 3 times 10 to the negative seconds. 2 to the n, 10 to the negative 8. But if I go up to 100, 2 to the 100th is 400 billion years at your current MacBook speed. The quantum computing idea, Roman, would make this faster. A lot. That number? That number is longer than the runtime of the universe. Now, all of these stars, I only have to get to 1,000 items to make exponential complexity longer than the lifetime of the universe. Millions, billions, trillions of pieces of data? I'll never search these. This assumes 2 things: current processing speed and single processor. So what's another cheat I can use here? Parallel processing, right? But then, how many processors do I need? Remember, every time I double the number of processors on a chip, I'm going to reduce this n by 1. If 100 of them, a task list of size 100, is 4 times 10 to the 11th years, a task of size 99 is 200 billion years with 2 processors. 4 processors, it's 100 billion years. I'm not going to get to a very small number of processors, number of years, but until I get a crap ton of processors, aren't I? So efficient algorithms are hard to come by. Finding them, writing more efficient algorithms is a more complicated process. But the overarching result is still there are some barriers to our computing ability. We just don't know how to surpass it. Questions? Some of these algorithms are best described recursively. As Sammy said on Monday, there are a lot of these that work best in that fashion. CS341, algorithms analysis, will dive through the way you look at algorithms in a much deeper fashion. I will tell you that on 3 different times, students have come back to me to ask about reviewing for just this chapter because their Google interview questions were all about Big O. This is as far as I'm going to go in chapter 3. So that means we've done all of chapter 2 and all of chapter 3. That's way too much for me to add anything else to it to add to an exam. That means a week from today is our second exam. You say it's 5 sections in chapter 2, 3 sections, that's plenty. There was 8 sections on the first exam, 8 sections on the second exam, like the symmetry. But that means it's Friday. Now, I actually have a meeting immediately after this class on Friday, so we're gonna be tight for time. That means can't go over by too much. I'm writing a reasonable exam, I believe, but my definition of reasonable and yours might be far apart. I guarantee you the exam will be in this time frame. Between now and then, we do have 2 other sections. I'm going to start chapter 4, but I'm going to do to you this coming Monday the same thing I did last Monday. That's why I said on Monday we'll start talking about pen testing, because we're going to have another teaching demo on Monday. My lecture for Monday is already recorded and waiting for you. And we have homework due on Monday for chapter 3, section 2. So I will collect that, and I will see you all then. I hope you have a wonderful rest of your day. Write it down. 12 minutes early. Write it down. If you came in late, please come get your homework. Tell them I'm taking attendance today. If I still have it, you're not here.